All right, let's dive into something pretty cool today. We're going to go on a little bit of a mathematical adventure. We're going to take a fact that is so simple, so obvious, something you learned, way back in elementary school, and we're going to tear it down to its absolute foundations to see what makes it tick.
So here it is, the central puzzle for today. We all know this, right? Any number times zero is zero. But what if I challenged you to prove it? And I mean really prove it. No multiplication tables, no calculators, not even your gut feeling. Could you actually prove it's true using nothing but pure logic? Well, that's exactly what we're going to do. So to really tackle a question like this, we've got to throw out everything we think we know. We can't just wave our hands and say, well, it's just obvious. See, in math, the most obvious things are often standing on top of this really beautiful, really intricate foundation of rules. And to prove anything with certainty, we have to start right there, at the bottom. So, where do we find these rules? Well, for this proof, we're going to step into the world of vector spaces. Now, I know that sounds kind of heavy, but don't worry. For what we're doing today, just think of a vector space as the game board. It's the arena, and it comes with an official rulebook that we absolutely have to follow. It gives us the structure we need to build our proof one logical step at a time.
So what is a vector space? At its heart, it's just a system with two kinds of things: objects we call vectors and numbers we call scalars. But here's the crucial part. Everything in this system, every single thing, has to play by a super strict set of rules, maybe 8 to 10 of them. These rules are called axioms, and you can think of them as the absolute non-negotiable truths that everything else is built upon. Let's meet our two main players here. On one side, you've got vectors. These are the objects of our game. The easiest way to picture them is as arrows, with a certain length and pointing in a specific direction. And on the other side, you've got scalars. These are way simpler. They're basically just the regular numbers we all know and love. Their job is to scale the vectors, to make them longer, shorter, or even flip them around. Okay, so this is it. This is our official rulebook. This is our entire toolkit. We don't need to memorize the whole thing, but just look at what these rules, these axioms, are doing. They're telling us exactly how vectors and scalars are allowed to play together. And pay close attention to rule number 5, the distributive property. That one's going to be our star player in a minute. Remember, these are the only tools we're allowed to use, nothing else. All right, the stage is set. We've got our rulebook, we've got our challenge. Let's build this thing. Let's see how these abstract-sounding rules can lead us to a solid, undeniable truth. Okay, back to the big question. Using only the rules we just laid out, how do we prove that any scalar, a, times the zero vector, 0, has to equal the zero vector? Let's get to it. Let's walk through the logic together, step by step. We start with what we're trying to figure out, a times 0. Now, one of our rules says that the zero vector plus itself is still the zero vector, right? So we can rewrite our expression as a times 0 plus 0. Now remember that star player, rule number 5, the distributive rule? We use it right here to break this up into a times 0 plus a times 0. So now we have this equation, a times 0 on one side equals a times 0 plus a times 0 on the other. And the final move? We just cancel one a times 0 from each side. And what are we left with? 0 on one side and a times 0 on the other. And boom, we've proved it.
And how cool is that? We didn't just say it was true. We didn't rely on intuition. We literally built this truth from the ground up, piece by piece, using only the rules we were allowed. It's a perfect, beautiful example of what mathematical rigor is all about. Okay, so now that we're all warmed up, let's take this logic and apply it to something a little more complex, but just as important. We're going to tackle something called the zero product property. So what does this even mean? It's actually pretty simple. It says that if you multiply a scalar and a vector together, and you get the zero vector as the answer, then one of those two things you started with had to be 0. You can't just multiply two non-zero things and get 0 out of thin air. This rule is super important because it stops all sorts of weird paradoxes from popping up later on. So how are we going to prove this one? We're going to use this awesome, kind of sneaky logical tool called proof by contradiction. The strategy is really clever. We're going to start by assuming the opposite of what we want to prove is true. Then we'll show that this assumption leads us to something completely ridiculous, a logical dead end. If our starting point leads to nonsense, then the original thing we wanted to prove must have been true all along.
Okay, here's the game plan. We're told that scalar a times vector alpha equals 0. Now for the contradiction part, let's just assume for a second that a is not 0. Our mission is to show that this forces alpha to be 0. Now, a key rule about scalars is that any non-zero number has an inverse, something you can multiply it by to get 1. So let's multiply both sides of our equation by this inverse. On the left, the a and its inverse cancel out, just leaving us with 1 times alpha. And on the right, we already proved that anything times the 0 vector is just the 0 vector. So we're left with 1 times alpha equals 0. And our rule book says that 1 times any vector is just the vector itself. So alpha must be 0. We proved it.
So this brings us to the big question, right? Why? Why go through all this trouble to prove something that just feels obvious? What's the point? It all comes down to one word: rigor. These formal proofs guarantee that our entire system of math is solid, consistent, and doesn't have any hidden cracks. And this isn't just for fun. This certainty is the absolute foundation that modern engineering, physics, and computer science are built on. Think about it. When someone designs a skyscraper or writes the software that runs our banking system, they are betting everything on the fact that these fundamental rules are 100% predictable and will never, ever break. Proving the obvious makes sure the whole skyscraper doesn't fall down. So, it leaves us with a fascinating question to chew on. We just saw how a simple fact like a times 0 is 0 is standing on this deep, logical foundation. What other obvious truths in our lives, whether it's in science or logic, or even just our daily habits, are built on a hidden, elegant framework that we just never stop to look at? It's pretty interesting to think about. Thanks for joining me.